Today, we're looking at the entirety of complex numbers. Now, this is a topic exclusive to the higher level part of the IB Math AA syllabus. So, if you're SL, do feel free to skip the video. To start off, why do we even need these new numbers? Well, think back to quadratic equations. Sometimes, when you try to find the roots, you hit a roadblock. The discriminant was negative, meaning you needed the square root of a negative number. We were told there were no real roots, but what if there were other kinds of roots? That's where complex numbers come in. To deal with the square root of -1, mathematicians defined a new number called the imaginary unit, denoted by the letter I. It's defined as I squared equals -1, or the square root of -1 equals I. This simple definition unlocks a whole new part of mathematics. With I, we can now find the square root of any negative number. For instance, the square root of -16 isn't a problem anymore. Square root of -16 equals the square root of 16 times -1, which equals the square root of 16 times the square root of -1, which equals plus or minus 4i. Numbers like this, 4i, -i, or pi times I, are called pure imaginary numbers. What happens if we combine these with the real numbers we already know? Well, that's how we get complex numbers. A complex number, which we often write using the variable z, has a standard form called the Cartesian form. Z equals a plus bi. Here, a is called the real part of z, written as re of z, and b is the imaginary part, written as im of z. Notice the imaginary part is just b, not bi. If the imaginary part b is 0, we just have a regular real number. If the real part a is 0, and b isn't, we have a pure imaginary number. So the set of complex numbers, denoted by c, actually includes all the real numbers r plus all these new numbers. We can visualize complex numbers on a 2D plane called the complex plane, or Argand diagram. The horizontal axis represents the real part, and the vertical axis represents the imaginary part. So the complex number, a plus bi, corresponds to the point, ab, on this plane. Now, associated with every complex number is its complex conjugate. This is written as z bar, or sometimes z star. You just flip the sign of the imaginary part to find this. So, for example, if you've got z equals 3 plus 2i, then its conjugate will simply be 3 minus 2i. The idea of a conjugate will become really useful in a moment, because we can now ask ourselves, how do we do arithmetic with these new numbers? Addition and subtraction are very straightforward. You just combine the real parts together and the imaginary parts together, just like combining terms in algebra. So 3 plus 4i plus 6 minus 2i equals 3 plus 6 plus 4 minus 2i, which equals 9 plus 2i. Multiplication also works like multiplying binomials. Use a distributive property, like FOIL, and remember that crucial fact that I squared equals -1. Division is where it gets a bit trickier. We don't really have a direct way to divide by a plus bi, but we do know how to divide by a real number. This is where our conjugate comes in handy. Let's take a look at what happens when you multiply a complex number by its conjugate. The result, a squared plus b squared, is always a real number. We can use this to our advantage. To divide z2 by z1, we multiply the top and bottom by the conjugate of the denominator, z1 bar. This makes the denominator real without changing the value of the fraction. Finding the multiplicative inverse, z to the -1, or 1 over z, is just a special case of division, where the numerator is 1. Now, the binomial theorem, which we learned for real numbers, works for complex numbers too. You can expand a plus bi to the n using the same formula, treating a as one term and bi as the other. Cartesian form, a plus bi, is great for addition and subtraction, But there are other ways to represent complex numbers that make multiplication, division, powers, and roots much cleaner. Let's go back to the Argand diagram. Instead of using the coordinates a and b, we can describe the point using its distance from the origin, r, and the angle it makes with the positive real axis, theta. The distance is called the modulus of z, written as the absolute value of z. From Pythagoras' theorem, it's easy to see. The angle theta is called the argument of z, written as arg z. We measure it counterclockwise from the positive real axis, usually in radians. Using basic trigonometry on the triangle formed by the points 0, 0, a0, and ab, we can find that a equals r cos theta, b equals r sin theta, tan theta equals ab, and theta equals arctan ab. Now, we can write z in terms of r and theta. Since a equals r cos theta and b equals r sin theta, we substitute these into z equals a plus bi to find z equals r cos theta plus I r sin theta, which is equal to r multiplied by cos theta plus I sin theta. This is called the polar form. We sometimes shorten it using the notation cis theta, which stands for cosine plus I sine. So we'd have z equals r cis theta. Let's try an example. Why bother with polar form? Because multiplication and division become incredibly elegant. If you have two complex numbers, z1 equals r1 cis theta, and z2 equals r2 cis theta, to multiply them, you multiply the moduli and add the arguments. To divide them, you divide the moduli and subtract the argument. Notice how the argument behaves like exponents, adding when multiplying and subtracting when dividing. This isn't a coincidence. It leads us to perhaps the most beautiful connection in this topic, Euler's formula. This formula connects the exponential function ex, trigonometry, and the imaginary unit I. Using Euler's formula, we can write the polar form even more compactly. This is called the Euler form or exponential form. Now, those multiplication and division rules make perfect sense using exponential rules. Euler's form is incredibly powerful. Now what about powers? If we want to find z to the n for some integer n, using the multiplication rule repeatedly, or just using exponent rules with the Euler's form, this gives us de Moivre's theorem. Essentially, to raise a complex number to the power n, you raise the modulus to the power n and multiply the argument by n. So, for example, de Moivre's theorem is fantastic for integer powers, but it also opens up the door to finding roots of complex numbers. What if we want to find the nth root of a complex number w? That means we're looking for all complex numbers z such that z to the n equals w. Let w equal big R times cis phi, and we're looking for z equals small r cis theta. Using de Moivre's theorem, z to the n equals small r to the n times cis n theta. So, we need small r to the n times cis n theta equals big R times cis phi. This implies two things. Small r to the n equals big R. So, small r equals r to the 1 over n, which is the positive real nth root. Number 2, n theta equals phi. But wait, angles repeat every 2 pi radians. So n theta could also be phi plus 2 pi, or phi plus 4 pi, and so on. Generally, n theta equals phi plus 2 pi k for any integer k. Therefore, theta equals n phi plus 2 pi k. This gives us the formula for the n distinct nth roots of w equals r cis phi. Why only up to n minus 1? Because when k equals n, the angle becomes n phi plus 2 pi n, which equals n phi plus 2 pi, which gives the same complex number as k equals 0, so the roots start repeating. There are exactly n distinct nth roots for any non-zero complex number. Geometrically, these n roots all lie on a circle, with the radius r1 to the over n, and they are equally spaced around the circle, separated by an angle of 2 pi over n. A particularly important case is finding the roots of unity. These are for the solution to z to the n equals 1. Since 1 equals 1 cis 0, the nth roots of unity are the following. These all lie on the unit circle, modulus 1, and are equally spaced vertices of a regular n-gon inscribed in the unit circle, with one vertex always at the point 1 when k equals 0. And that's complex numbers for IB Math AAHL. It's quite a lot of content, so don't worry if you don't get it first try. Feel free to rewatch certain parts of the video, and of course do lots of practice. Pure imaginary numbers,